without filling in every last detail, filling in most of the details here, and by analogy here, we're going to ignore some more details for the moment. We'll come back and fill those in, but this is going to get kind of difficult to visualize. It's going to be difficult to visualize r theta space transforming into xy space and giving us the surface area. We've certainly made plausible the following claim, so I'm just going to state it like this. From what we've done so far and from the expression we have here, we can make another small step and make a claim about how we get the surface area. Okay, so I'm going to put it this way. And then a miracle occurs. And we conclude that the surface area is double integral of r sub r cross r sub theta. We're going to take the magnitude, okay, because again, actually r sub r cross r sub theta is a vector, and when we stated this, we should have said the magnitude of this product gives us the area. So we should say magnitude of this vector cross this vector is the area. We know that the magnitude of the cross product of two vectors is the area of the parallelogram they define. Now, that's with respect to r and with respect to theta. We'll get into the gory details of why you don't have r dr d theta. I'll simply note that this is not an area increment. If it was supposed to be an area increment, we'd have an r dr d theta, but the r part is really kind of taken up in the process of finding the cross product. In other words, that r is taken care of in a way that's a little bit challenging to understand. Now, we'll try to draw that out. But for right now, we have just another integral for the surface area. And at this point, nothing so far has depended on r and theta being polar coordinates. We've never once mentioned any relationship that depends on these being polar coordinates. The only important quality of the relationship of r and theta is simply that the two vectors that we get in the xy plane by the x sub r I plus y sub r j and x sub theta I plus y sub theta j vectors not be parallel. That's certainly not true if these are polar coordinates, but it's not true in general if we just put a few simple restrictions on our coordinate system, on the nature of the r and theta coordinates. So this whole process can be generalized to x of uv I plus y of uv j plus z of uv k, where u and v might well be polar coordinates r and theta, but they might well be any other set of coordinates that satisfy some simple conditions of independence. And if those conditions are met, the surface area is simply the double integral of the magnitude of RU cross RV du dv. Everything we've said allows us to replace r and theta with u and v. Again, with just a simple restriction on the fact that these two vectors here essentially can't be parallel. The two vectors we get in the xy plane by changing u a little bit and by changing v a little bit cannot be parallel, which requires simply that these x, y, and z functions of u and v have to be, in a sense, linearly independent. Within that context, we're going to return to the original problem.